Hello everyone, welcome back to Labtube. In this video, I'm going to do question 2 from the section 16.8. The question asks to use the Stokes theorem to evaluate the surface integral of curl of f ds, where the vector field is given here, x squared sine z, y squared, and xy. And the surface is part of the paraboloid z equals 1 minus x squared minus y squared that lies above the xy plane. And it is oriented upward. Okay, so to solve this question, you need to know what is the Stokes theorem. Stokes theorem says, that flux of curl of a vector field over surface S. So flux of curl is this on a surface S is equal to the work that is done by the vector field on the boundary of that surface. So this is boundary of that surface, and F dot dr. Something very important here you have to notice is that these are integral of vector fields, either on surface or on a curve, along a curve. In both cases, you need orientation. For this one, you need orientation. For this one, you need orientation. This equality is true if the orientation, if the boundary of S, I show by that. In your book, they wrote C. If the boundary of S is oriented positively with respect to orientation of the surface, the orientation of this. Okay. So if you choose the right orientation for the curve, instead of doing an integral of vector field over a surface, you need to do just a line integral of a vector field, which makes things easier. Okay, so let's see what is our surface, what is its boundary, what is the orientation, and what is the right orientation for its boundary. First thing to see is that it says it is a paraboloid. So let me have this x, y, z. Paraboloid of the form this 1 minus x squared minus y squared. Okay, I draw this by red one. Okay, so paraboloid of that form would be upside down first, and it will be up by 1. Okay, that's the paraboloid, that's the surface. And then it says the orientation is upward. Orientation is upward means at each point is like that. Okay. Now, the first thing is that to see what is the boundary of this thing, this surface. It says it's just part of the paraboloid which is above the xy plane. So our surface comes down up to the xy plane. So the boundary is going to be the intersection of the paraboloid and xy plane. And how do you get that? It is the intersection of z equals 1 minus x squared minus y squared. That's the paraboloid. And xy plane is given by z equal to 0. So you set these two, and then you get x squared plus y squared equals 1. It is a circle. It is the circle centered at origin with radius 1. Okay, what about the right orientation for the boundary? So let me write this is boundary. The boundary is this guy. Okay, what about the orientation? The boundary should be oriented positively with respect to the orientation of the surface. What does it mean? It means that if you stay up like the orientation of the surface is up, so in this case I have to stay like this on the line, okay? And when you move in a direction on the curve, the surface stays on your left, okay? In other words, so this is pointing upward like this, and as I move this way, I will have that thing. So if I am here going this way, if I go this way, this is up. The orientation of surface gives me up or down. So this is up. And then if I move in this direction, the surface stays on my left. So that's the orientation. Okay, but what does it mean in this case? So this is x, this is y. Okay, and as you can see from the picture, I start from x and go to y. That's the direction. So you start from x, go to y. Start z, x, go to y. That's the direction. That's the direction of the boundary, which is positive with respect to the orientation of the surface. Okay, now everything is set up because I have a curve, and instead of doing integral of curl of f ds over s, I can use Stokes' theorem and just integrate over the boundary of the surface f dot dr. Okay. So I have f, my vector field is here. I have to find the vector, a parameterization for my curve, for my boundary. As you can see here, my curve is circle, and it is counterclockwise, and we know that the orientation, the parameterization for such curve with that orientation is given by x r theta is equal to cosine theta sine theta. That's x and y. I'm using polar coordinates. And then for z, I know that this happens at the level of z equal to 0. So this is the parameterization. What about theta? Theta goes from 0 to 2 pi. Okay, now everything is ready, and I know that to evaluate such integral, I have to apply these steps. First, write boundaries for your parameters, 0 to 2 pi. Then write the vector field in your parameter. It means that for x you plug in cosine theta, for y plug in sine theta, for z plug in 0. Okay, let's do that. If I plug in z0, this will be 0, so that is 0. For y, I plug in sine theta, so sine theta squared. And for z, the third component, I plug in x times y, which is cosine theta sine theta. Sine theta, cosine theta. Okay, then I have to dot product it to r prime. So I have to find r prime. That's r prime is minus sine theta cosine theta 0. So I have minus sine theta cosine theta and 0. And now I can evaluate that, because if you dot product this to that, you're going to get a function theta, and this is just a regular integration. Let's do that. 0 times that's 0, sine squared times cosine. So I have sine squared theta cosine theta. The sine theta cosine theta times 0, it is 0, so I have just this. It's a regular integral, and you have to evaluate that. To evaluate that, you can use substitution. Set u to be u to be sine theta, its derivative here, and it is going to be it is just regular integral. So it is going to be 1/3 of sine cube theta going from 0 to 2 pi. And if you plug in, actually we are going to get 0 minus 0, which is equal to 0. Okay? So in summary, the question asks to evaluate this double integral, surface integral of curl of f ds using Stokes theorem. We know that Stokes theorem says that curl of f ds, this integral, surface integral, is equal to the line integral of the vector field along the boundary of the curve, the surface. And we have to be careful about orientation. So what I did here, we found the boundary, we found the orientation for the boundary, and then we found the right parameterization for that. And then by Stokes theorem, I changed my surface integral to line integral to evaluate line integral. Maybe probably I have to write down here, to evaluate line integral, you have to do 3 steps. Plug in your parameterization into your vector field. Instead of dr, you find r prime and dot product it to f, and then d theta, and put boundaries of your parameter. Okay, we did that, and then we got this integral, which is regular integral, and we evaluated, and the value was equal to 0. Thank you for watching this video.